I've been in networking for over a decade and decided to make some content to try to help others understand this industry. Let's finish up the subnetting discussion. This is not a very complicated concept at a high level. We take a large network and we divide it into smaller networks. The idea is pretty simple, but understanding the binary, the function of the subnet mask, the network ID, the broadcast address, the usable address range, that's where a lot of the complexity is. So please review the previous subnetting videos if those concepts are unclear because we're going to put all of those things together now. The largest network for IPv4 would have a subnet mask of all zeros or 0.0.0.0 or /0 in CIDR notation. This means that all bits are host bits since every bit in the subnet mask is a zero, and we would have one network. The number of unique addresses would be 2 to the power of 32 because we have 32 bits that are host bits. That would translate to 4,294,967,296. Now, because we have a network ID and a broadcast address, we would only be able to assign IP addresses to 4,294,976,294 endpoints. The next largest network would be if we had one network bit in the subnet mask. So that would have a subnet mask of 128.0.0.0. This would also be a /1, and we would be able to have two networks in this case. So the number of unique addresses would be 2 to the power of 31 because there would be 31 host bits. So we have one network bit, 31 host bits because we have a total of 32 bits. So 2 to the power of 31 would be 2,147,483,648. So the next mask down is if we use a subnet mask with 2 bits. Then the mask would be 192.0.0.0 or /2. And since there are 2 network bits, the number of networks would be 2 to the power of 2. That gives us 4 networks. Since 2 of the 32 bits are network bits, that means we have 30 bits that would be used for host bits. So the number of unique addresses would be 2 to the power of 30, and then that calculates to 1,073,741,824. So we can see as we add more network bits, we get more networks, but fewer unique addresses per network. We also have to keep in mind that with each network, the number of usable addresses is reduced by 2 because one address is reserved as the network ID and another address is reserved for the broadcast address. So let's look at this from the other extreme. We've looked at only 0, 1, and 2 bits that being network bits. So let's go to the other side of the spectrum and see what happens if all of the bits are network bits in the subnet mask. That would be a mask of 255.255.255.255 or /32 network. The number of networks would be 2 to the power of 32 because there are 32 network bits, or 4,294,967,296. Since there are 0 host bits, the number of unique addresses would be 2 to the power of 0, or 1. The next smallest network mask would be a 31. So if we have /31, that means we have 31 network bits, and then there would be one host bit. This would be a subnet mask of 255.255.255.254, or /31. And the number of networks here would be 2 to the power of 31. So this gives us 2,147,483,648 networks. With 31 network bits, there would be one host bit. So to calculate the number of unique addresses, we take 2 to the power of 1, and that gives us 2 unique addresses per network. If we continue this one more place, and we say we have 30 network bits in the subnet mask, That would be a subnet mask of 255.255.255.252 or /30. The number of networks is 2 to the power of 30 or 1,073,741,824 networks. If there are 30 network bits, then there would be 2 host bits. So the number of unique addresses is 2 to the power of 2, and that gives us 4 unique addresses per network. So as a quick side note, the /32 and /31 networks, they're kind of special cases. A /32 is considered a host network, and a /31 network can be used for point-to-point links. The reason these are special is that they do not require a separate value for the network ID or the broadcast address. So let's not get too far down that path right now because we really just want to focus on how the subnet mask changes the size of the network. So we're looking at the subnet mask length extremes to show that there is an inverse relationship between the number of networks and the number of unique addresses per network. As the number of networks increases, the number of unique addresses per network decreases. Let's look at a specific network and we can see how it can be split into smaller networks. So we're going to use the network 192.168.100.0, and we're going to use a subnet mask of 255.255.255.0 or /24. If this network is just left as is, there would be one network and it would have 256 unique addresses, and that would be because the fourth octet has values of 0 to 255. So that would give us 256 unique addresses. Like any other network, except for those 2 special cases we talked about, the /32 and the /31, this needs a network ID and a broadcast address, so the usable addresses, or the ones that can be assigned to endpoints, would be 254. So if we want more networks with fewer unique addresses, we add more network bits to the subnet mask. We have all of the addresses from 192.168.100.0 all the way up to 192.168.100.255 that we can use. So let's say for this example that we need 4 networks that have 50 unique addresses per network. To create 4 networks, we would need to add 2 more network bits to the subnet mask because 2 to the power of 2 is 4. If we only needed 3 networks, we would still have to use 2 more bits because we have to have at least 3. And where the bit boundary ends up is we can have a 1, a 2, or a 4 based on the binary. If we needed 6 networks, we would have to divide it into 8 because that's the next bit boundary would be at 8 bits. So now we have 26 network bits instead of 24. If there are 26 network bits, then that means there are 6 host bits. To find the number of unique addresses, we take 2 to the power of 6 and we get 64. So we can't forget that each network loses 2 addresses for the network ID and broadcast address. So that means that we only have 62 usable addresses for each of these 4 networks. So we said that we needed 50 addresses per network, and we have 62 usable IPs with this subnetting. So it looks like we've met the requirements for this use case. If we didn't have enough usable IPs, then we would need a larger starting network to then split up because we need a larger pool of unique addresses in order to carve them up into the sizes that we're looking for. So now that we know that we can use a /26, we need to identify the 4 networks that we have divided from the original 192.168.100.0 with that 24-bit mask. We need to identify the 4 networks we've created by making this a /26 network. So here we can see the binary in that top line of 192.168.100.0. That was the network ID of the /24. The 8 bold bits there in the last octet, those were host bits in our starting network. But we're taking those 2 bits, the ones that are red there, and we're going to make those network bits So now we have the 6 host bits at the end of that octet. And now we have 2 more network bits. And these help designate the network ID. So if we look at those, our combinations of 2 bits, the values are 00, 01, 10, and 11. So the 4 network IDs that we can create from this, because we have to add those binary values in the last octet that are bolded in red, we have to add those to our network ID. So the first network we've created is 192.168.100.0/26. The next one would be 192.168.100.64/26. Then 192.168.100.128/26. And then finally 192.168.100.192/26. So these are the network IDs for the 4 new networks. They all have a subnet mask of 255.255.255.192 or /26. The broadcast address for network 1 would be 192.168.100.63. That's what we get when we turn all those host bits on. The broadcast address for network 2 is 192.168.100.127. And the broadcast address for network 4 is 192.168.100.191. Sorry, that was network 3. And then the broadcast address for network 4 is 192.168.100.255. And I notice in here I have 192.160 instead of 168 in the second octet. So don't let my typos throw you off. That should be 192.168.100 for the first 3 octets of all these. So now we can see that every unique address, once we add in the ranges between there, because our usable range is between the network ID and broadcast address. So for network 1, we're using all the unique IPs from 0 to 63. Network 2 is using all the IPs from 64 to 127. Network 3 uses all the IPs from 128 to 191. And network 4 uses all of the IPs from 192 to 255. So we've used up all of the unique addresses that we started with in that /24 network that went from 0 to 255. We've just carved them up a little bit differently now into more networks with smaller usable IPs per network. So subnetting is creating smaller networks from a larger one by adding more network bits to the subnet mask. This creates more networks that have fewer usable addresses per network.